So today we're covering L'Hopital's rule. Now, here's what it is. There's two forms of it. If the limit is x goes to a of f of x is 0, and also the limit is x goes to a of g of x is also 0, then this limit, the limit of the quotient, is equal to the limit of the quotient of their derivatives, okay? So this one right here is of the form 0 over 0, okay, because both of these are, both f and g are going to 0 according to this. So this one right here is the same thing except there's infinity. So it's infinity over infinity. Okay, so now taking 0 and divided by 0, that's what we call an indeterminate form. Indeterminate form. Okay. So basically, to apply L'Hopital's rule, and you need to have one of these two forms. Okay, you need to have one of those two forms, and these are indeterminate forms where 0 over 0, you don't quite know what that's going to be, because we know, for example, if you take the limit as x goes to 0 of sine of 2x over x, okay, remember we talked about this one, and I think we did some problems similar to this, so the answer was 2, right? Now, if you take x to 0, that sine of 0 is 0, and that's going to be 0. So this is going to be 0 over 0 when you do that. And so if you apply L'Hopital's rule, now L'Hopital's rule is not to apply the quotient rule, not the quotient rule. Okay, it's simpler than that. It means if you have this, you can only do it if you have this, that you take the derivative of sine x, okay, which is just 2 cosine 2x, and you take the derivative of x, which is just 1. Okay, so you're not thinking quotient rule here. You're just taking the derivative of the numerator and putting it out in the numerator, taking the derivative of the denominator, putting that in the denominator. Now you can plug in a 0 there, and that's 2 is the answer. Okay, so that limit is 2, just like we had figured out before, and we discussed that before. Okay, now you can also do that when the limits of f and g are both infinity. So you have the infinity or infinity, you can apply that there. Okay, and so here, these are indeterminate forms, and this is where you can apply, with these two forms, you can apply L'Hopital's rule directly. Okay, now there's other forms, and these are other forms right here. Okay, so so for example, this one, 0 to the anything is just going to be 0, and then anything to the 1 is just, wait a minute, 0 to the, no, this is not an indeterminate form. What am I thinking? I don't think that one is. Okay, so 0 times infinity, infinity minus infinity, 0 to the infinity, 1 to the infinity, infinity to the 0. Let me look that up really quickly. I don't think 0 to the 1 is indeterminate. I think I should have written 0 to the 0. Why did I write that there? Okay, yeah, it's not indeterminate. It's not an indeterminate form, because that's just going to be 0. Okay, if you just worked that, that's just going to be 0. Now, if you take 0 times infinity, okay, 0 times anything is just basically 0, but infinity times anything is basically infinity. So when you're looking at limits like this, then it kind of depends on how fast it's going to 0, how fast that's going to infinity, and kind of have to balance that out and figure out what that is. Same thing here, infinity minus infinity. this one of these infinities could be quote larger or smaller than the other one, or maybe they're the same. Just depends on how fast, because these are limits. Okay, 0 to the 0. Okay, 0 raised to anything is typically just going to be 0, but then anything raised to the 0 is going to be 1. So you kind of have to see which goes how fast is going to one or the other. Same thing with 1 to the infinity. 1 raised to anything is just 1. But if you take something that's just like a teeny tiny bit larger than 1 and you take it to a large power, then you can get a large number. And also here, same thing here. Okay, so these are indeterminate forms. Now there's things that aren't indeterminate forms that you have to be careful for. Okay, but let's go ahead and look at some exercises here. And number 1, to try to get through that point right there, we're trying to identify what's indeterminate forms and what isn't. Okay, so it says evaluate if they're not indeterminate forms. If they are indeterminate, then we put indeterminate. Okay. So this limit is 0, that limit is 0. So we have this is 0 over 0, and that's indeterminate. And if we know what the limits of the derivatives were, then we could apply L'Hopital's rule to find what this is. That might help us to get it. Okay, this one right here, f of x is going to 0, and p of x is going to infinity. Okay, so here we have 0 over infinity. Well, 0 is really small, infinity is really big. You take something really small and divide by something big, that's just going to get you something really small. So that's just going to be 0 in the end. Okay. Okay, now let's see. H is 1, and p of x is infinity. So you take 1 divided by infinity, that's going to be 0 also. Okay, and so then this last one, p of x is going to, let's see, infinity, and q of x is also going to infinity. Okay, that's indeterminate. And if we might be able to find using L'Hopital's rule. Okay. So sometimes, you know, even though you have infinities and ones and stuff in the expression, when you plug it in, sometimes you can just determine what it is. And sometimes you can't, though, because they kind of like work against each other. Okay, number 2a. Okay, so here we have f of x goes to 0, and g of x goes to 0. So here we have 0 to the 0. And that one is going to be indeterminate. It's one of the indeterminate, what the heck? Indeterminate. Okay. Here we have f of x going to 0, p of x is going to infinity. Okay, if you take a number that's really small and you raise it to a large power, then, you know, like if you had, like, for example, if you had like 0.1 and raise it to the 10th power, that's going to be 0.000, a bunch of zeros and then a 1. So that's just getting smaller. So that's just going to be 0. That's just going to converge to 0. Okay, next one, h is going to 1, and p of x is going to infinity. Okay, this is going to be indeterminate. And that could be, like, basically be anything between 0 and infinity is what that could end up being. Okay, this one right here is actually equal to the f of, you got p of x, which is infinity, and then f of x is 0. Okay, that's also indeterminate because Yeah, why is that indeterminate? Okay, so infinity is a really large number, but if you raise it to a small number, like if you take like 1,000 raised to the 0, that's just going to be 1. Okay. But it's important to realize that these are not, it's not taking infinity to the 0. It's really a limit. It's something that's approaching infinity over something, to raise to something that's approaching 0 and seeing what happens. Okay. So if this is going to infinity very slowly and this is going to 0 very quickly, then this could be just 1. Okay. It's going to just being 1. But on the other hand, if it's going to infinity very quickly and this is going to 0 very slowly, it could end up being infinity. Okay, or anything in between. Okay, this one right here, p of x is going to infinity, and q of x is also going to infinity. Okay, well, this one's just going to blow up to infinity. Okay, you're taking something that's going to infinity and you're raising it to a positive power, and you're just increasing that power, then it's just going to go to infinity faster. Okay, this one right here, you've got the q root of p. Q is going to infinity, and p is going to infinity also. Okay, so the infiniteth root of infinity. This is sort of how you think of it. It's not exactly what it is. That could be the same as infinity to the 1 over infinity, or infinity to the 0, which is indeterminate. Okay. Great, let's move on. Let's actually do some problems with this. So when you got a problem to do like this, the first thing you want to do is plug in and see what happens. Okay, so if you plug in a 0 in the numerator, you get, so let's just put it over here, we get e to the 0 minus 1 in the numerator. The denominator is going to be sine of 0, and that's going to be 1 minus 1 in the numerator, and then 0, which is going to be 0 over 0. Okay, so this is indeterminate. So that means we can apply L'Hopital's rule because we have this form. So we can apply L'Hopital's rule. So you're going to take the derivative of the numerator. Okay, the derivative of e to the 5t is just e to the 5t times the derivative of 5t, which is 5. And then this is minus 0. And then over here, as you go to 0, this is going to take the derivative of sine t, that's cosine t. And now, if we plug things in now, we got 5 e to the 0. That goes away over cosine 0. E to the 0 is just 1, so that's 5 over, and then cosine 0 is just 1, so 5. Okay, so 5 would be the answer to that one. Okay, moving along to the next one. We have 1, and the numerator is 1 minus sine of pi over 2. And in the denominator, we have 1 plus the cosine of 2 pi. Okay, sine of pi over 2 is 1. Cosine of 2 pi is a negative 1. So we have 0 over 0. That means that we come back here and we apply L'Hopital's rule. Yay. Okay, so the derivative of the numerator is, that's 0, so I could ignore that. Derivative of negative sine theta would be negative cosine theta. Okay, derivative of cosine theta would be negative 2 sine theta, or 2 sine 2 theta. Okay, so yeah, derivative of cosine is sine. And then by the chain rule, I have to take the derivative of 2 theta, which is 2. Or rather, the derivative of cosine is negative sine. Okay, now these negatives are going to cancel, so let's just go ahead and wipe those out. Or maybe yeah, let's wipe, okay, let's wipe those out. Actually, yeah, I'll wipe them out. Like this. I'll wipe them out like this, though. Okay. So now we plug in the pi over 2. So we have cosine of pi over 2 up in the numerator, and the denominator is 2 sine of, because if you put pi over 2 in here, you're just going to get pi, right? And cosine of pi over 2 is 0. Sine pi is also 0. Okay, so now here's something that might happen when you're doing the homework, is you'll apply L'Hopital's rule and you'll get 0 over 0 again. Okay, so what you're going to do in that case is you're going to apply L'Hopital's rule again. Okay, so apply again. Okay, so we'll do that right here. We'll apply that right here. Okay, derivative of the cosine is negative sine. And the derivative of sine is cosine. So, but you have another 2 coming out, so that's going to be 4 cosine of 2 theta. And then when you do this one, when you plug in the pi over 2, you're going to get negative sine of pi over 2 and 4 cosine of pi. And sine of pi over 2 is 1, and cosine of pi is negative 1, so that's going to be negative 4. Okay, so the answer is going to be 1/4. Okay, so this is applying L'Hopital's rule twice to get the result. Okay, let's take a look at some more. Number 5. This is limit as x goes to infinity. Okay, so here the numerator is going to infinity, and the denominator is going to negative infinity. Okay, so that's also L'Hopital's rule. Let me point out, though, that we already have another way of doing this one. And let me just show you really quickly how that I've already showed you how to do these ones, but probably a lot of people forgot. Let me just show you really quickly how you do it without L'Hopital's rule. Then we'll do L'Hopital's rule. So if you multiply everything by 1 over x squared, or just multiply by this fancy form of 1. Okay, this is just 1. All that. And okay, then distribute that in. Then in the numerator we have 1 over x plus 1. And in the denominator we have 5 over x squared minus 3. And as x goes to infinity, what's going to happen is this and this are both going to just go to 0. And you end up with negative 1/3. Okay? Which is the answer. Okay, but now let me show you how to do it using L'Hopital's rule. And so we take the derivative of the numerator. That's 1 plus 2x. And the derivative of the denominator, that's 0. This is going to be negative 6x. And still, it's going to infinity over infinity when you take x and the x is to infinity. So we apply L'Hopital's rule again, and you have 2 over negative 6, which is going to be negative 1/3. Okay, so either way, you get negative 1/3. Okay, let's look at the next problem, number 6. So you're taking the limit as x approaches 0 from the right of this. And the inverse tangent actually goes to infinity as you approach from the right. And the natural logarithm goes to negative infinity. Okay, so so L'Hopital's rule can be applied. Okay, now the derivative of the inverse tangent is, okay, so let me just bring this to your memory here. The derivative inverse tangent is 1 over 1 plus x squared, right? So the derivative of our inverse tangent of 5x will be 1 over 1 plus 5x squared times the derivative of 5x, which is 5. So it's just going to be a 5 up here. The derivative of the natural log of x is 1 over x. Okay, we should rearrange things. This 1 over x kind of comes up as an x right there. Okay, and as x goes to 0, this will go to 0. That goes to 0, and this also is going to go to 0. So you basically have 0 over 1, which is going to be 0. Okay, so that's just applying L'Hopital's rule. Okay, so all of these are direct applications of L'Hopital's rule. Now let's get into how we handle some of the other indeterminate forms. Okay, so over here, okay, maybe it's better if I write this as, well, okay, so as x goes to infinity, x to the 6th is going to, it's basically, you got infinity to the 6th. And then this one is going to go to e to the negative infinity. To the 5th. But basically what you have here is infinity times 0, because that's going to go to 0 and that's going to go to infinity. Okay, this is another indeterminate form, but we can't apply L'Hopital's rule directly. So what you have to do is manipulate this. And manipulate this expression into infinity over infinity or 0 over 0. That's what you have to do. And in this case, it's not too bad. In this case, they pretty much fall right into your hands because this e to the negative x, I mean, you might already have the instinct to just write it as e to the x to the 5th, and then 1 over that. Okay, so the negative, if you have a negative exponent, that means you can just put it to the denominator, and then without the negative. Okay, and now we have infinity over infinity. Okay, so that means we can apply L'Hopital's rule. So we'll go ahead and do that. And the derivative of x to the 6th is 6x to the 5th. The derivative of e to the x to the fifth was going to be e to the x to the fifth times the derivative of x to the fifth, which is 5x to the fourth. Okay, and we can cancel this one with 4 of those, which will leave just with an x in the numerator. Okay, and so then we still have the numerator going to infinity and the denominator going to infinity. So we can apply L'Hopital's rule again. Okay, the numerator, derivative of the numerator is going to be 6. The derivative of the denominator is going to be e to the times another 5x to the fourth comes out. So that's going to be 25x to the fourth right there. And this one, when you look at it, it's 6 over the 25 times infinity to the fourth, and then e to the infinity to the fifth. Okay, that's just basically 6 over infinity, which is going to be 0. So the limit there is going to be 0. One interesting thing that could happen is, let's say you had like the limit as x goes to infinity of x to the fifth over e to the x. And then you can start taking, because that's infinity over infinity, right? Now with this one, it's 5x to the fourth over e to the x. And it's still infinity over infinity, so you can do it again. But you can kind of see what's going to happen. You can kind of see ahead, because this denominator, e to the x, didn't change at all when you took the derivative. And then, but then this x to the fifth reduced by 1 power. So this is becoming weaker as we apply L'Hopital's rule. And so you can kind of see in the end, we're just going to get 5 factorial of e to the x. If you repeatedly apply that, and then it's got some finite number of infinity, which is going to be 0. Okay, that's just the kind of interesting thing that could happen. Okay, let's look at this one right here. As you're going to 1, this is going to, wait just a second. Okay, this is going to, okay, you're gonna have a 0 in the denominator, so that's basically infinity. And this is also gonna have a 0 in the denominator, so that's basically gonna be infinity. Okay. So here we have infinity minus infinity. And so this is another indeterminate form, but we can't apply L'Hopital's rule directly to this. We have to manipulate, again, so we need to manipulate this. And again, into infinity over infinity or 0 over 0, one of those two. So the way that we're going to do it is, when you have one fraction minus another one, then get a common denominator and combine. Okay, so that's going to be the strategy. Okay. So limit as x approaches 1. Dang, I forgot to put this down. But this should be, dang, that's bad notation. It should be there. Okay, like this. Okay. So we're going to take this first one and we'll multiply by log x over log x. And we'll take the second one and we'll multiply that by x minus 1 over x minus 1. Okay, so we get that. Okay. So this one is, we multiply this one by log x over log x. We multiply this one by x minus 1 over x minus 1, and then you'll end up with this, because they both have the same denominator, and so you just combine them like that. Okay, so let's simplify this a little bit and kind of see what's going on. So we have 5x log x minus 5x plus 5. And then down here we've got x minus 1 log x. Okay, now as you go to 1, as you approach 1, what happens? Just plug a 1 in. Log of 1 is 0, right? So that's going to be 0. And then minus 5, as you putting a 1 in there, plus 5. And then down here we have 1 minus 1 times log of 1. So that's going to be 0, and that's going to be 0. Okay, so you have 0 over 0. So yay, we get to apply L'Hopital's rule. Okay. Let's take the derivative of the numerator. So the derivative of this will be the derivative of this first part, which is 5, times that part, plus 5x times the derivative of this part, which is 1 over x. And then the derivative of that is minus 5. Okay, now in the denominator, we have the derivative of this first part, which is, derivative of this first part, which is 1 times the second part, plus this first part times the derivative of the second part, which is 1 over x. Okay, let's try to simplify things. These reduce, right? And then this minus this reduces to 0. So that's all 0. That goes away. Now, as you go to 1, this goes to 0. That goes to 0, and that all goes to 0 too. So you still have 0 over 0. But let's manipulate this because you don't have fractions right here. So we're going to multiply by x over x, and you distribute that in there. Well, I'm running out of space. Wait. Okay, so I multiply an x in, and I multiply an x into here. Like that. Okay, I still have 0 over 0. Or do I? Yeah, I still have 0 over 0. Because that's going to be 0, that's going to be 0, and this is going to be, when you plug 1 in, that's 1 minus 1, which is 0. Okay, so L'Hopital's rule. We're running out of space. Okay, so the derivative of the first part is 5 times the second part, plus the first part times the derivative of the second part. Okay, and then down here we have the derivative of the first part is 1 times log x, plus x times the derivative of the second part, which is 1 over x, and then plus the derivative of x is 1, and the derivative of 1 is 0. Negative 1 is 0. Okay, so let's simplify. Let's see if we can simplify this. Okay, so that's 5 log x plus 5. Yay, that's not 0 anymore. Yay. And then down here we have log x plus, and this is 1, and that's 1, so plus plus 2. Okay, and so then this and this are going to both go to 0 as x goes to 1, because log 1 is 1. Log 1 is 0, I mean. And so you're going to be 5/2 is going to be the answer. Okay, so this is interesting where you have infinity minus infinity. We got common denominators, applied L'Hopital's rule twice. We had to simplify some things along the way, and in the end, it's 5/2 is the limit. Okay, let's look at number 9. Here you're going to infinity. Okay, so this first part's going to be infinity, and this is also infinity if you plug this stuff in. Okay, because the limit is x to infinity of log x is infinity. Okay, so what we need to do is manipulate into 0 over 0 or infinity over n infinity. And when it's minus like this, okay, on this problem, they actually walk you through this one on this exercise. This is a weird exercise. So they walk you through it, and basically, what you're going to do is factor out a 5x. Okay, so out of everything. Okay. So factoring a 5x out of there gives you just 1, leaves you with 1. And then factoring 5x out of here is like kind of weird. You'd be like, some people will be like, whoa, there's no 5x there. Well, just put a 5x in the denominator. Just make it so that when you multiply this by this, you get that. Okay, and there you go. Okay, that's the first step. Okay, now what you have is infinity times, and then this is 1 minus, as you go to infinity, this goes to, this is actually going to go to 0, by the way. You actually have infinity times 1. Here's what you have. Okay, now, but let me kind of explain that though. I guess the book explains it, so we need to explain that. So we'll do a little note right here. The limit as x goes to infinity of log x over 5x. Okay, this part right here. I'm gonna explain why that goes to. I'm sorry. Why this goes to 0? Why it goes to 1? I'm sorry. Wait. Blah, what am I thinking? Okay, this goes to 0. Okay. Okay, so that's this right here goes to infinity, and the denominator also goes to infinity. So L'Hopital's rule. The derivative of log x is going to be 1 over x, and the derivative of 5x is going to be 5. Okay. And so here you have 1 over infinity, that's going to be 0. Okay, so that is going to go to 0, which means that you've got infinity times 1, which will be infinity, will be the limit. Okay. So hopefully you can get that one. Okay, number 10. Okay, so here, what you have here is if we plug a 0 in, here we get 1. Okay, and then a 0 here, you get 1 over 0. So you, basically, it's 1 to the infinity. And that's indeterminate. Okay, now if to handle exponents, okay, so to handle exponents, take logarithms. Okay, so you want to do, this is how way you do it. Okay, so when it's exponents, so I mean exponent is like 1 to the infinity, or any of the other indeterminate forms that are exponents like that has something power raised to another one. Okay, so what you do is this. You let L stands for limit. Capital L stands for limit. One minus 6x to the 1 over x, okay? And now, so I let L equal that. That's our limit. Now I'm going to take logarithms. The natural logarithm of L is equal to the limit, as x is to 0, of the natural logarithm of 1 minus 6x to the 1 over x. Okay, now, the reason that I did logarithms is because now this exponent, by the laws of logarithms, this exponent is going to go out in front. Okay, and so what I end up with here is, you know, because this goes out in front, that means that x goes to the denominator. I end up with that. Okay, and now this is infinity over infinity. And I can apply L'Hopital's rule to this. Okay, so apply L'Hopital's rule. Okay, so that means we're going to take the derivative of the numerator, which is 1 over 1 minus 6x times the derivative of this inside by the chain rule, times the negative 6. And then over here it's 1. Okay. Okay, up here I have a negative 6, and down here I have a 1 minus 6x, because this is just a 1. So this goes to the denominator here. And now when I go to 0, this is just going to go to negative 6. Okay, but this is the natural logarithm of the limit is negative 6. So I apply exponents to both sides. I exponentiate both sides. And I have the limit is e to the negative 6. Okay, and so that will be the answer. So this limit is e to the negative 6. And that's the answer. Okay, and then this last one here is the same thing, but let me see. Okay, so you have infinity So here I have x going to infinity. So this is infinity, and then 5 over infinity, that's like infinity to the 0. So this is an exponent like this one was. So we're going to take natural logarithms, okay? But you're going to let L be the limit. Oops. As x goes to infinity of x to the 5 over x. That means the natural logarithm of L will be the limit as x goes to infinity of the natural logarithm of x to the 5 over x. Okay, so it's a nice thing that the natural logarithm can just go inside the limit like that. And then, of course, the next step would be you want to take this out in front, right? So you end up with 5 log x over x. Okay, because the 5 over x comes out here. That's the 5 over x right there, and like that. Okay, and then so now, again, you have infinity over infinity as x goes to infinity. That goes to infinity. That's what is that. So L'Hopital's rule. Derivative of 5 log x is 5 over x. Derivative of x is 1. And so this all goes to 5 over x. So you basically have 5 over infinity, which means it's going to be 0. But you have to remember that that's the natural logarithm of the limit. So the limit is actually e to the 0, which is 1.